Okay, so welcome to our Maths Mastering How to Help at Home Parent Workshop. We will go through as much as we can just about the approach and how we can help at home, but also just to give you an idea of the way in which we do things and why we do things in the way that we do. So first off, we got what we use in order to help it. So a lot of you, if you have any idea about maths, know that it's changed over the course of the last couple of years. The new national curriculum came in 2014, and it kind of changed the benchmark for where children needed to be for each year group. Because of that, there was a big look at how they were going to go about teaching that and increasing the level of demand for children. And they came up with what's called a mastery approach. What they realized was there was a big difference between children who were just taught the process of maths, how to get from a question to an answer. And that's called the process. And what they were finding is they were getting a lot of children higher up in school that could do the process, but didn't understand why it worked or how they could use that knowledge. And they found that the top end of education, when you get to A-level and secondary and university, they struggled. English taught mathematicians struggled. So they changed the approach and they look at different ways of teaching it, and they looked at maths mastery as a way of doing it. And what maths mastery's aim is to make a really firm understanding that underlies and underpins all of the learning that happens on top. We use White Rose Maths here, which if you want to go and have a look at, go and search for White Rose Math. They've got lots and lots of stuff on their website and stuff that you can also use to help at home as well. There's a lot of information on there they put over lockdown, which was a really good thing for that. Yeah. And we use the other two to help alongside that, because it's rather than always rely on one thing, you want to make sure you take the best from a selection. So maths mastery, the idea behind it is that it's a lot of thinking that goes around it. So what you have is a thread that runs through the entirety of a lesson and the entirety of the year, which links into the entirety of the school. But each of those steps are broken down to really small chunks, so the children understand the thinking behind it. Now, if you understand why you're doing something, you can then take that bit of knowledge and use it in lots of different ways. The way we do that is we look at lots of different areas. So that coherence is the journey that travels all the way through in small steps. We then think about representation and structure, and this is about how we show what we're trying to do and how we access that understanding. So it's looking at patterns and making connections and that sort of thing. We have the thinking set of skills, which is all to do with how we talk about it as well as how we think about it. So understanding comes into that. The fluency is the bit that is really much easier to practice, because that's the bit that the quick knowledge, the quick recall that we can get really helps us understand and makes the conceptual leaps we have to make for each step much easier, because we don't have to think back about bits of knowledge that we already know. And in that comes our number facts, our number bonds, times tables, and all that sort of thing. Because if you know that and don't have to think about it, you can use that knowledge very quickly to make the conceptual leap to the next bit of learning. And then variation. This is about the different ways you ask questions and different ways you see questions being asked to you. And this is both procedural and conceptual. So procedural is just the steps to get to the answer, whereas conceptual is the understanding you have. That's the idea. That's why I chose maths mastery for going through maths in the school. The aim of maths mastery is that all children within their year and as they progress through primary are equipped with this really deep and secure knowledge of mathematical concepts. But it's not just one way of doing things, it's also adaptable. And what that means is that they can take whatever they understand and use it in lots of different situations. Rather than just having one method of doing things, they've seen a number of different ways to get to the same answer. And the problem we sometimes get in maths is that you look at a question and you go, I can't do that, because you've only been told one way. Well, in this case, what we're looking at is showing them lots of different ways, and they can use any of these methods to get to the answer, because actually the mathematical thinking behind it is the same. It's just the way in which their brain works is easier. And as soon as you can understand one way, the next couple of ways become easier as well. So if you're thinking about really low down, this is in reception level, the facts of number of 5 being 3 and 2, it's not just that 3 and 2 make 5, or that 5 is 3 and 2 put together. It's also understanding what 5 is and how that can help. And this relates much higher up as well. If we're thinking about bridging through the number 10, this comes up in year 2. And when you think about this, you're thinking about, okay, so why do I need to know that if I'm adding 7 to 16, I can add 7 is made up of 4 and 3. I can add 4 first to get to 20, and then the 3 to make it 23. We all do that, or majority of people do that naturally, but children need to be taught it in order for them to understand that they can do it no matter what. And that helps later down the line, because when we start using our formal written methods, that knowledge makes it much, much quicker to do each independent column that gets us to the answer, because it's quick, it's easy, and it's already in our heads. So these things have to be taught early on for them to be able to get there. Now, one part of maths mastery, or an important part, is the approach that you use. And we use a concrete, pictorial, and abstract approach. And what this means is that you are doing something, you're seeing it, and you understand the abstract part of it at the very end. So what it does, it helps gives that deep understanding. So we give children the concrete resources and they can investigate a concept first. If they haven't had to play around with number, then they don't have a firm, secure understanding of it, and they can't manipulate it in the right way. So you do this before formal methods are introduced, and it's really about, actually, if we have a really firm understanding of number and the mental ways to do things, it makes our life much easier later on. And when we come to formal methods, we understand why they work. Not just, I can plug this in and it gets me to the answer. I understand why that helps and why I'm doing it. Then you've got the pictorial stage, both of which, the concrete and the pictorial, run alongside the abstract. So the pictorial stage is the next step. You take an idea which you've shown or used a concrete resource for, and you draw a picture which helps you understand it, or you show symbols in order to help you understand it. This is really useful because actually much later on, when you come across a mathematical problem, it's much easier to understand what the problem is if you can see the problem rather than not know what it's asking you. So it's that visualization of a problem and visualization of how to find the solution. In each of these stages and all of these stages, that concrete and that pictorial representations run alongside the abstract, which is the thing that we normally see, the numbers and the symbols. And because you do both together, it then helps the child understand where that thinking comes from and what that is actually showing them. Because you have both parts, it does make them much happier when they make that leap to just using abstract, because they've got that firm understanding beforehand. So some of our examples of concrete resources we use across the school, and we don't just use these low down the school, you use them all the way through, because when you come to a difficult concept, and I've used it for algebra at times, very easy for that, because having an unknown and not showing something, they can easily see if you just hide it. And then they understand that actually that's the unknown. So we've got things like Numicon, very useful. The other thing is this pattern recognition. So they don't just they don't have to count it each time, they can recognize the pattern, which helps them. Counters and tens frames. So each of these are blocks of 10, because our number system is base 10. It makes it easier to count. And I'll show you another one of that later, an actual example of it. Counters, easily manipulated, can be in different colors, can be used to represent different things as well. We've got lolly sticks can be used, and they can be used individually or they can be bundled. I've got an example later on I'll show of a very different way of using it, which helped the children understand it. Multi-link or cubes, again, very useful for showing a visual representation of a problem. You can say, okay, I've got a string of 10 here, or I've got 7 of one color, 2 of one color, and 1's another color. All of those numbers make 10 in the end. And by breaking it down and using it in those ways, you can show lots of information that way as well. You've got number beads. Again, these are split into 10. So it's good for counting tricks. So counting on in 2s, 5s, and 10s. These are very good for that because you can physically move them, or you can group a lot. So if you take 20 away, you can group them into groups of 4, for example, and then you can see how many groups you have, which is the start of multiplication and division. You have sticks. This can be done in lots of different ways, but the really useful thing about this is just the ability to take, when you get to 10, is to make a bundle of 10, and they can physically see that that bundle, every bundle is 10, and each one on its own is 1. So actually 10 ones make a 10, and then you can also, if you get a rubber band big enough, put 10 10s together and have 100. It's a really nice visual representation of how our number system works. We've got a place value grid, which you'll probably all have seen before, but in this case, it's also linked to counters. So it's very easy then to use counters in different ways. And you can have actual counters with numbers on them, which will work in those, which we have as well. Then you've got counting bears, or sorting bears. These are used further down, and it's for non-number recognition. So it's all about pattern seeking and trying to make the most of what you can see within a pattern. And it really helps, especially lower down, them just working out that it doesn't matter what I'm counting, I still count in the same way. It doesn't matter whether they're lined up or grouped, it's still the same number no matter how I see it. And it really helps with that subitization of a number, which is knowing a number in and of itself. The multiple different representations help. Dice, which we've all seen before, but very useful for representation, also random number generation. We've got deans, which you may remember, and these are split into 1s, which are the blocks, 10s, which are 10 of those small blocks together, 100s, which are 10 of the 10s put together, and the 1000, which is the 3D representation. And if you put 10 hundreds together, you get the same thing. Children are always amazed by that, and you can actually show it to them, which is quite good. Dominoes, which are used again for number recognition, very quick recognition of number. You can see the pattern of the dots. You can use it on both sides. So if you take a domino, you've got a 1 and a 3, you can say, okay, that's a 4 domino because the 2 together make it. So you can look at number bonds within it. Very quick, very easy way of testing number bonds to lots of different numbers. And obviously it goes up to 12 in this case, but you can use the same pattern for other times. So an example of this, if we were looking lower down the school, we're looking at solving 7 plus 4. The way you might go about it is to use a model, and like I said before, we use it alongside the abstract. So we'd have both parts. This is using a tens frame. So in this case, we'd put 7 counters in one tens frame, and we'd put 4 counters in another tens frame. That's 7 and 4. And then there are multiple ways to do this. They could just count them. But as we were talking before about bridging through 10, you can also show them that you can fill in the rest of the tens frame, which makes a full 10, and then you count how many you have left over. And it shortens the calculation you have to do because you can recognize that one block is full, which is 10, and you only have to then count the rest of them, which then makes it to 11. And it's a really nice visual way of them showing it, and obviously can be used in a pictorial representation, much like I have done here. It's that link between the two and the abstract that helps children understand why that's working and how you bridge through 10. Now we have lots of different representations that we use. So if we were looking at dividing, and this comes up higher up in the school, so 13 divided by 4, we know it's 3 remainder 1. But there's lots of different ways we can show this. So we can do counters into a bar model, and we share them out evenly into the different bars, and make groups of 3 with 1 left over. And then we can say that there are 4 groups of 3 with 1 left over. We can also use a place value grid. So we put 13, 1, 10, and 3 1s. Because we can't split the 10 into 4, we move them across and then group them easily into groups of 4. We can see we've got 1, 2, 3 groups and 1 left over. And that's the difference between grouping and sharing. Sharing, you share at a time. Grouping, you put them together. And then we can use Numicon. So here's our 13, and then we're dividing by 4. So how many 4s will fit into the same amount? Well, you can line up the 4s and you can even put them on top and see that you can easily fit 3 of them in, and you can see that there's 1 left over. So even using Numicon, which is used further down, actually you can physically represent and show how it might work for a more difficult question. Division is always the one that people look at as the most difficult operation. If the other thing we have is different representation of the same thing. So this is a tens frame, and you can see the counters being used here to represent different numbers. We have a part-whole model, and this is really useful for addition and subtraction or partitioning. And what you say is, in this case, we've got 10s and 1s being 2 of the parts, and we put them together and you can physically move them. And as you move them up, you can see you've got 2 10s and 4 1s together, and that's 24. The same goes for 100s. We can have 3 parts that all link into 1 whole. And these go together to make the whole. So you can also do it the other way around. If you have the whole, you can split it into multiple parts, and those parts then help us think about either addition or subtraction. If you're missing a part, the children should know it's subtraction. If you're missing the whole, it has to be addition, because the parts go together to make it. You can see we can then use a part-whole model alongside a place value chart, so that link as they go through for the different representations, which is really important for the children, because they then have an understanding of where the thinking comes from and the links between it as we go. Here's our lolly sticks used for representation of Roman numerals. So again, it's just used a physical thing. They're actually doing it. If you're doing something, you're more likely to take it in because you have to physically doing it. It's taking more processing power to do. And then an idea of this is one of our tables down in year 2, which has all of the different systems that they're used to seeing. They've got a place value grid. They've got a part-whole model. They've got a tens frame, and they've got an area to write their abstract, and they've got all of the tools they need on the table to help them do it. And this is used during free flow to let the children explore and use all of the tools that they're used to using in a maths lesson themselves, and it gives them more ownership over their own learning. So how can we help at home? So in Key Stage 1, it's really important that children have a really firm understanding of number and what each number is and how we can use it to our advantage. So things that you can do, you can help her learn number facts and bonds. And this is the sort of thing we were talking about what 2 numbers go together to make another one. So 3 and 4 go together to make 7, so does 2 and 5. And it's really pulling apart those numbers. And actually, realistically, you only need to know those bonds up to 20, because the pattern remains the same going beyond that. So you can use the same pattern again and again and again throughout the number system, and it always remains the same. So it's really far down, really low in our school, that actually those skills, that secure knowledge of number, really comes out. Doubling and halving is really useful, especially low down. They can do that with physical objects. They can do it drawing, or they can do it in their head. And it's just realizing that actually to double, I just put 2 of the same numbers together, and halving, I split them in half, sometimes leaving me with 1. Counting on in 2s, 5s and 10s, and starting to think about those times tables. Counting on is slightly different than times tables, because counting on is repeated addition and goes through and just gets us used to the pattern. Times tables are a little bit more a little bit more interesting than that, because you also can link them through to division as well, whereas counting on, it's slightly harder to link through to addition. Then you've got practice number formation, making sure that the numbers are formed in the right way, and that's a really key thing. Quite often I see 3s and 4s the wrong way round, and it's quite useful just to quickly fix that early on, so it's not something that hangs over them, not something that forms a barrier for them. And then matching the words to the numbers. This is 1, can you show me a 1? Or this is my digit 1, can you show me the word 1? Just very easy things to do that help. If you are doing it with them, try and use it in everyday situations, things that they can help you with. Oh, can you lay the table? How many knives and forks do I need? How many plates do I need? That's your counting in 2s or number recognition. Linking it to real life, things that they feel actually there's a purpose for this math, there's a purpose for me doing this. They could help you with the shopping, they could do all sorts of things like that. Making it fun or a game that's more interesting to them. There are lots of those sorts of things online as well that you can use to help you top marks. So a website has lots that they can use as a game to do. But it just means that they don't see maths as boring or something that they have to do. It's something that they find interesting. Times Tables Rockstars is a brilliant example of that. And the other one is talking about the days of the week and months. And actually, it's quite important on how many days there are in the months, because it forms the basis for our understanding of time. And time is seen as part of maths because it is a method of calculating how long something takes. Going into Key Stage 2, things that you can do, again, very similar to Key Stage 1, we're looking at mental methods of manipulation of number bonds. So it's those quick, easy questions that they can do in their head. Now, realistically, what you're looking at is numbers between 1 and 100, rather than having to rely on a formal written method for. They should hopefully be able to use their mental methods to do it. They can add the 10s on, they can bridge through 10 with their units to find the next number, because that's so much quicker and so much more efficient than writing it down. It does take practice, and it does mean that they have to think about it, but you can easily fix that in to when you go shopping, for example, and you're saying, okay, if you want that toy and that toy, that's going to cost this and that's this, how much are they together? They have to tell you rather than you tell them, or you give them a limit and they have to work out what they can get. It's those sorts of things that children don't realize is helping them with their maths, but actually is. Times tables, massively important, because actually times tables helps them no matter how far they go through life. Times tables really does help because it's nice and quick and easy. You can get to an answer. Really does help with not just multiplication but division, because you should know your division facts that go alongside those. And I'm pretty sure if you've spoken to any of your teachers during parents' evening during in Key Stage 2, they would have talked about knowing your times tables, because it really helps not just with timesing and dividing, but also fractions, area, volume, all of those come up within times tables. And a lot of them, the number manipulation happens within those times tables. Practicing the written methods, I'll go through some examples of those slightly later on as well. And then talking like a mathematician, and I'll show you a few STEM sentences which will help with that as well. Try and use it in everyday situations, much like before, and linking it to real life and making it fun. This is the same across both Key Stage 1 and Key Stage 2, because actually, if they can see it being used all the time, it's just helpful for them. Shopping and money, they're more likely to use money or going to have to use money as they go up through school, especially when they go to secondary school and have to buy their own lunches or whatever it happens to be. They need to have a working knowledge of that. So if they can help you do that sort of thing, that's really great. And then we get on to telling the time. The only times they actually see telling the time realistically is years 2, 3, and 4. By the end of year 4, they should be able to tell the time, both analog and digital, which means that they really need a lot of practice. So anytime you can get them to tell you the time, or, oh, how long is it going to be until we can play on, watch TV, or whatever happens to be, I can do it in 20 minutes, what time would that be? They then have to use their knowledge in order to help them get to the answer. If we're thinking about stem sentences, we think these are all the sort of things that we can do. So I think that is the answer because I know this, or I already know this, so this might be my answer. That it didn't work because of this, so I did this instead, or I noticed that this was the pattern. These all help our mathematical thinking. It helps our reasoning skills as to why we've made that choice or why we've decided it's wrong or not. It also helps with that understanding that it doesn't matter if we get it wrong. If we get maths wrong, that's fine, as long as we know that it is wrong, and then we can ask for help in order for us to correct the mistake. Because let's face it, at some point in our lives, we're always going to get something wrong. We need to know that it's okay. We just need to learn from it. And some of the best learning experiences come from the mistakes that we make. And then in Key Stage 2, they will start to be introduced the formal written methods. I'm going to show you some examples from Year 6. These are the most complicated they get, and obviously they get easier as you go further down, but they're building to this point. So what we might have is some representations of place value and addition and subtraction. And what you can see here is a few different ones. So we've got, here's a place value chart, and you can see how they link to each other and what the understanding of number is. So if you have 6 counters in the ones, that's 6. 1 counter in 10, that's 10, and 4 in the hundreds column is 400. Put it together, you get 416. It just helps understanding of how that number comes together, and the manipulation of it helps at that point too. And then we've got a few examples of what are called bar models. And what these are is basically like the part-whole model. The top of it normally, or part of the model, will show the total, the whole answer put together. And then your 2 parts make up that number. And that's why they are the same length, because they have the same value, both the bottom and the top. And the same goes for all of those. If we're looking at addition, you'll notice something different that I've done here, and this is just the way I find it easier to. First off, it is different from every other method, so it's easier to have a different method for each one, so you have less confusion over which operation you're doing, but also gives importance to that number. And what you see is I've left a gap. So you should all know, obviously you can deal with each column independently. So I can do 4 and 3 in the ones, that gives me 7, 0 and 6 gives me 6, 3 and 2 gives me 5, 2 and 1 gives me 3, and 1 here on its own gives me 1. But what happens when we come to a number that crosses the boundary? So in this case, 4 and 8 actually make 12. Now, quite often when people do that, they either put the 1 down here, a little 1 out of the way underneath the answer, or they put a little 1 up here above the answer. And sometimes these are actually relatively easy to miss. So by giving it the same importance as the rest of the numbers, by giving it a square to itself, they know that they have to deal with it, and they know that it's part of the addition, which is the thinking behind it. And therefore you're less likely to lose any of the additional parts that come off of it. And this works really, really well as we go forwards and starts up, can start lower down. Subtraction looks slightly different. So subtraction, we make sure we don't need that gap because we're not going to carry or exchange one to the next column. And then we can just look at how we do our subtraction per column. So 4 minus 1 is 3, 6 minus 0 is 6, 3 minus 3 is 0, 4 minus 3 is 1, and 1 minus nothing is 1. And then if we have to cross the boundary, which we sometimes have to do, what we're able to do is exchange from the column 1 above it. This column is worth 10 of the column below it. So I can take 1 away from this column. So this 6 becomes a 5, and then it's carried down to the next column as 10 because it's worth 10 of that column. And that makes that 14. At which point then I can do 14 minus 6, which is 8. And this is really useful because quite often children, unfortunately, go, okay, 4 minus 6, that's 2. Because what they do in their head is they take the small number away from the big number. And we can't do that with subtraction. Subtraction has to be in the order that it's asked to be done. It's not commutative. We do come across problems that come up like this, where we can't exchange from the one above it because there's nothing there. So we have to go up until we can exchange down, and then do each step as we come down until we get to where we can use the number. I call this the domino effect because it rolls down. Other people just call it exchanging, my little bit, but it just makes sense to me. And then we've got multiplication. This is long multiplication, as this is what we do in year 6, but the premise is the same. What you're doing is timesing by the units, each digit by the unit. So 2 times 4 is 8, and then 9 times 4 is 36, which is there. And again, what you'll see is this 3 then that we're adding to the answer is different from our addition, so it looks different. It doesn't confuse us in the way that we go about doing it. We add that 3 to our next answer, which is 4 times 8. So we can keep, which is 32, plus a 3 is 35, and keep going that way. And what we've also done here is when we times by the 10, we are automatically timesing by 10 first, which puts that 0 in the first column, moves them all along 1, rather than adding a 0, because we do move them along 1 column. Then we can just times by 8 each of the digits, and they fill in the right column because we've already moved them along 1 column by timesing by 10 first. And the same works, timesing by 100. And then we've got long division or short division. The children have quite a good understanding of short division as we go through, and it's the one that they're taught if they ever do get outside of school. The problem is that they don't understand where it comes from, and where it comes from is our long division method and the way in which we do that and the way we go about it. What you'll notice is actually these numbers are quite hard, which is why we're using them. So 17, we don't necessarily know our times tables for 17. So what we do is we say how many 17s fit into the hundreds, which is 43, and then we can have 34, which is 2 lots. Then, and we keep going down until we say each one. And what we're doing is bringing down the column that our answer is going to be in. So when we're looking in our tens column, we bring that down, we see how many 17s fit in, which is 5, and that answer then goes in our tens column 2. Then we go into our ones column, we bring down the number from the ones column. We know we're answering our ones because we brought that one down. We see how many 17s go in, and what you can see on the side here is our repeated addition just to help us out. We can go 1, 2, 3, 4. Okay, we can fit 68 in, but not 65. So that's 4 lots of 17. So my 4 goes up here. I can then take away that from what's left, and I'm left with 7. I can't make any more groups of 17, and that makes it our remainder. So what we're looking at is lots of different ways of doing things. What I will say is that what we will do hopefully towards the further on in the year is have another session which is then split into 3. So we have our key stage 1, we have lower key stage 2 and upper key stage 2, and hopefully a reception if I can manage it, which will be more specific to that need of that particular age group. Because we've got such a wide group here, it's much easier then to make it applicable to everyone. Okay. Thank you. And I will leave it there.